Welcome to the squeeze theorem. So the idea here is that sometimes we have functions that we can't use our basic limit properties and our special limits to evaluate. So sometimes we run into limits for which the special limits and basic limit properties are not enough to evaluate. So one thing we can do is we can try to trap the function we don't understand between two others that we do. So by this, I mean, let's say that we have a function which is kind of just all over the place. And it's squiggling back and forth and back and forth and back and forth and back and forth, and we don't really know for sure what's happening. Well, if we can trap that function between two others that we understand, and if we can show that both of those functions are approaching the same point for their limit, so here I'm going as x goes to 0, then the one we didn't understand must also be going to that same point because it's being sort of funneled in. So essentially we're trying to show that we have a funnel around a function we don't understand that funnels our function into a point for our limit. So officially, what the squeeze theorem says is, suppose that let's go with, we're looking at a function f of x, and let's see that f of x is trapped between g of x and h of x on an open interval I, containing c, and then let's suppose that we have that the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x is equal to L. Then what we get is that the limit as x approaches c of f of x is also equal to L. So our job here is to evaluate the limit of, as x goes to 0, of x squared times e to the sine of 1 over x. So some things that we have trouble with, recall as x goes to 0, 1 over x goes to infinity. Right? And sine just oscillates over and over and over and over again as we work our way to infinity. So sine oscillates forever. So what this means is that sine of 1 over x is going to oscillate. As x approaches 0. So this is a situation, sine of 1 over x itself, as x goes to 0, is just going to go crazier and crazier and crazier, oscillating. And then e to the sine of 1 over x will also bounce around, will also oscillate. Now, sine oscillates from -1 to 1. So this will be between -1 and 1. So sine of 1 over x will oscillate also between -1 and 1. So e to the sine of 1 over x is going to oscillate between e to the -1 and e to the first, or e. So i.e. 1 over e and e, like crazy. So it'll be bouncing around between 1 over e and e. So e to the sine of 1 over x itself doesn't have a limit. It's just going to bounce around. So e to the sine of 1 over x will be one of those graphs that just goes, oops, it's not actually negative, sorry. Will just oscillate crazily and then spread back out. The question though is, what happens when we add in that times x squared? So now if we add in the x squared, we were looking at the limit as x goes to 0 of x squared times e to the sine of 1 over x. So we know, we just talked about the fact that e to the sine of 1 over x is just between 1 over e and e. So this part here is oscillating, but it falls between 1 over e and e. So 1 over e is less than or equal to sine of 1 over x. Sorry, e to the sine of 1 over x is less than or equal to e. So now what if we just go ahead and multiply that all by x squared? So if we now multiply by x squared is positive, so it does not mess with the inequality, or at least non-negative, so it does not mess with the inequalities. So we have x squared times 1 over e, or 1 over e times x squared, as less than or equal to x squared times e to the sine of 1 over x, as less than or equal to x squared times e. So here we have our function is trapped between 1 over e times x squared and e times x squared. So we know that x squared times e to the sine of 1 over x is trapped between one over e times x squared and e times x squared. So if we looked at a graph, we have 1 over e times x squared and we have e times x squared. Both are positive, both are 0 at x equals 0. So this is 1 over e times x squared, and this is e times x squared. And we know that our other function is oscillating between those, going crazy, but it's trapped in the funnel. So if we look at this picture, as x goes to 0, our funnel on both sides is coming into 0, so our function itself appears to be coming into 0. And we can just verify for ourselves. We have then, we know that the limit as x goes to 0 of 1 over e times x squared that's a polynomial. We can just plug in. This is 1 over e times 0 squared, or 0. Similarly, the limit as x approaches 0 of e times x squared, that's a polynomial. We can just go ahead and plug in and evaluate. Is e times 0 squared. We again get 0. Both of these are equal. So we have, by the squeeze theorem, that the limit as x goes to 0 of x squared times e to the sine of 1 over x must also be equal to 0. So this is the squeeze theorem in play. It's convenient to work with. So those functions, especially the ones with oscillating, going crazy, the squeeze theorem definitely comes in handy for evaluating what the limit should be.